Okay. Hi, AP physics students. So yes, that was a bit of a bombshell that dropped last night. So here's what I think is going to happen. If I were to look into a very small, cloudy crystal ball, is that I think they're going to, for attendance, I think what's going to happen is that each day for like a half an hour, we're going to have like a Zoom meeting, kind of like class. But I think that's going to they're going to try and get that done before noon. So you'd have like half an hour for first block, half an hour for second, half an hour for third, half an hour for fourth. And that would be done by noon. So that's how you would take. That's how I would take attendance. So you every day you all would be expected to actually Zoom in during that time. Okay. Literally, and if you don't, I'm counting you absence, and then that starts a whole cascade of things. So obviously, I can't teach most of my lessons in a half an hour. So how I see that half an hour is answering any questions, kind of going over stuff for the day, whatever. Because there's going to be some big lectures coming up on planetary motion, gravitational fields, and they're just like they're literally like 2-day-long lectures. The good news is you guys don't have any homework during those days. Okay. The bad news is that I've got to talk and explain a whole bunch of formulas and things like that. So this actually isn't a bad unit to be on remote, mainly because it's centripetal motion and gravity. So the only lab that you have to do is the one that the other group started yesterday that I sent you out the data for, and then you guys are going to finish the data for the next set of trials. And so it's not a bad unit because the planetary motion stuff and gravitational fields, it isn't like, oh, here, let's build a satellite and launch it into orbit as today's lab. So it's not bad. And then we'll start the one over momentum, and then we'll get into Thanksgiving. So this isn't a bad scenario. Hopefully, after Thanksgiving, you all are back and we're here. So that's kind of what I see playing out. Now, and Party Girl and Rachel and Kelsey, you guys are just going to have to listen to this part. So over here, and let me explain this. So for those of you that have come in the front of the school, there was these memorial panels that are up in the front. And so, and I'll make this appear to the other half of the class as well. But this is something I wanted to say like in person and not just through a Zoom. Unfortunately, we have half the class gone. But so if you see like that big solar array that's out here on the west side of the school. So I went to the school board back in about 3 years ago. It was November of 2017. And I said, I know too much science. I know too much about what's going to happen with potential climate change to not do something. Because, I've never had my own kids. I've never been married. And I've taught here for like 30 years. And so this is a legacy that I wanted to leave. So let me go out. I've taught phenomenal kids. I've taught that have gone on to be very successful. So let me go out and try and raise $400,000 to build that system. And they said, hey, fine, knock yourself out, whatever. And so we really started fundraising in January of 2018. And then by summer of 2018, at that point, we'd raised about $140,000. So then, because of that, I was able to secure financing through another company that wrote the check, and then they took advantage of some federal tax credits. And so that's how the system got to be built. June 11th of 2019, it went online, and so during this time, it saved about $40,000 for the districts in electricity costs. So let me explain like the numbers that are up there, first, third, and fourth block. So what's become the tradition is that so this is like one of the panels, and so like this is my mom and dad's memorial fund down here, and then like this is one of my uncle's. This one where it says unless, this is from Katie Riffle. Katie Riffle is one of my former students, and Katie didn't want her name on the panel. Because if you just want to buy your own panel, it takes a donation of $740. And so Katie didn't want her name on there. But if you've ever read the book The Lorax, which is a great book, and one of the things in the book, in the back of the book, it says, unless people start to care an awful lot, nothing's going to change. It's not. And so Katie didn't want her name on there. She just wanted the word unless. And so that's where that's from. And so I've got like former students and some nephews and former teachers. And so what's become the tradition is that, and these were the first set of classes that when I started the project back in 2017. So like first block honors, physics, AP physics, 2017, 2018. And so I'm not going to expect, you guys to donate $740 because there's not that many of you. So what I do is I say, okay, if everybody donates the equivalent or donates $20 on average, $20, then what will happen is then when I build the next set of panels, then it will say AP Physics, 2020, 2021. So Rachel Meeker, shout out to Rachel, has already donated $20, so that's why you have $20 up there on the board of your total that you still have to donate. So it isn't just, it's obviously all of you that are in my AP Physics class. And so eventually we always have some really nice sweatshirts, if you've ever seen some of the kids wearing the sweatshirts and hoodies and stuff like that. So we have solar merch as well. And if you buy that, part of that money will go towards that fund as well. So it's an option, okay? I'm going to get this with my other classes as well. And that was something I wanted you to hear that, because the reason I did it was because of my dad. My dad died in '96, and Dad had to drop out of school after 8th grade because he had to go work on the farm during the Great Depression. And so, but Dad always stressed that you are a steward of the earth, and you leave the earth better than how you found it. And so, this was my contribution to try and leave the world a better place. And so, and it's like I said, it's a 200 kilowatt system. To give you some perspective, most schools, if they have them at all, they have 10 kilowatt systems. This is a 200 kilowatt system. It's the biggest solar array on any school, basically from the Canadian border with Canada the Canadian border with South Dakota. And if you go straight south all the way to Dallas, Texas, that's the biggest solar array on any school in the entire Midwest in this whole region. So it's pretty cool. And so the next goal is to try and get panels on other schools in the district as well. So that's kind of a long-term plan. And so that's where the next set of money is going to go to, maybe on Craig Woodman or May South High School or something like that. And that's kind of the long range plan. So collectively, you all kind of need to decide, hey, is this something that you want to do? Do you want to continue this tradition? If you don't want to, that's fine, okay? But every class, since I've started this, has always said, okay, hey, we want our names up there, so when we come back for our 10-year reunion or 20-year reunion, we say, yeah, that was my class. We were a part of this. And so that's the cool thing about the project is that, the kids can drive by and say, yeah, I helped pay for that, and that was my contribution. So anyway, that's kind of the spirit. All right, so let's talk about the lab. So I'm assuming that you all watched the video that I sent out yesterday, and and I also sent you the data for trials 1 through 4, which was collected by your compatriots. So here's the basic idea: is that you're going to swing a rubber stopper around, and then you're going to time 10 revolutions, and the weight of what's ever hanging down is going to be the centripetal force. Okay, so without rehashing that whole thing, that's what you've got going. So on trials 5 through 8, you're going to keep the same stopper, and you're going to keep the same centripetal force. I'd recommend that you all use maybe the 200 grams. Okay, I'd use that's a nice weight to work with. It isn't too heavy, it isn't too light. I just use 200 kilograms, which would be 1.96 meters. So let's just go with that. Okay, we're going to keep that as 1.96 meters. So what you want to do is you want to change the radius. So when you measure that radius, you want to measure from the center mass of the stopper to this edge. So you're going to measure from here to here, okay? Then, and I'm gonna have different colored markers on there. You wanna make, once you get that measured out with like a meter stick, so you can lay this out on a meter stick, maybe you wanna start with, I don't know, 0.4 meters, whatever that is. Then make a mark here so that when you're swinging it, you can see that mark. And when it gets to that mark, that's when you know you've hit that radius. But you obviously want to put maybe like different colored markers on here so that you're not getting them all confused with, you know, the other ones. So like let's say there's that mark that I want. So I'm going to get this thing going like this. And then when that mark hits there, then I know I've hit that radius, okay? And then we're going to time that amount of time. One person swing, I'd have two people counting, and then compare the times. The times should be pretty close together. So that's going to be that set. Then when you get to trials 9 through 12, then you're going to change the mass of the rubber stopper. So I have different size stoppers in there. You can even tie different stoppers together, you know, so maybe tie a small one with this one to change that mass. So here's the basic idea, is that you're going to look at centripetal force equaling mv squared over r. This is the mass of the stopper. This is how fast you're going. This is the weight of whatever's hanging down. That's the most important assumption that we're going to make. So when you get to, on page 2, okay, when you answer questions 4, 8, and 12, you want like a simplified equation. So out of 4, 8, and 12, 2 of these are always going to remain constant and 2 of them are going to be changed. So what you want to do is isolate the 2 that are going to be changed. So like on trials 1 through 4, that ratio of mass of the stopper to the radius is a fixed value. Oh, so that's centripetal force equals kV squared. It's a quadratic relationship. So what you want to do, and if you're not sure, ask me and I will tell you. So like on number 8, you want to simplify that so that you're going to, when you graph number 8, when you get down to when you do number 8, you've graphed velocity on the x-axis, or radius on the x-axis, and velocity on the y-axis. So that second one, you're going to put radius here, and you're going to put velocity, and it should go something like this. Okay, that's roughly what that graph should look like. So what you want to do is simplify mv squared over r. You want to isolate r. Okay, so I move r over here, and then I move that centripetal force over here. Mass is going to stay the constant. Centripetal force is going to stay the constant. So you have r equals, and then like whatever you end up with over here. Okay, so that's what you want to look at. What you'll see is that this is going to be like a square root function. Now, when you get to question number 13, you want to calculate the experimental error. So what you're going to do on number 13, and you're only going to do this for trials 4, 8, and 12. And so help me show these calculations. So you're going to go to trial number 4, and you're going to use mass of the stopper, v squared over r. This is how you're actually going to calculate that centripetal force. You're going to use the mass of the stopper, you're going to go to your trial number 4, you're going to look at your velocity, and you're going to divide that by the radius. And that's going to give you the centripetal force. So that's actually what you got when you did this. What you want to do on trial number 4 then is compare that to the weight that's hanging down. So what you want to do on number 13, okay, on number 13, you're going to go your theoretical minus experimental divided by theoretical times 100, okay? So in this case, so somebody got a calculator handy? Take 0.4 times 9.8, I think it's 3.92. Take 0.4 times, take 0.4 times 9.8, what'd you get? 3.92. So on trial number 4, the theoretical centripetal force is 3.92 newtons. minus what you get when you do mv squared over r divided by 3.92. Okay, so I cannot, here's the most important thing. This is the mass of the stopper. That isn't the 0.4 kilograms. This is the mass of the stopper. So you're going to do that for trials 4, 8, and 12. Now, when you get to number 14, you're going to calculate the centripetal acceleration based upon, on number 14, you're going to calculate centripetal acceleration equaling using v squared over r. You're going to go to trial number 4, you're going to look at the velocity, you're going to square that and divide that by the radius of 0.8. Now, your g's, and I tell you this, but you all are horrible at reading. To get the g's, you're going to take your centripetal acceleration and divide that by 9.8 meters per second squared, because it's a ratio. So if your centripetal acceleration is 19.6, you divide that by 9.8, oh, that would be 2 g's. So that's how you're going to get your g's. On number 15, okay, on number 15, you want to calculate the centripetal force needed to keep the Earth in orbit around the sun. So what I would recommend on number 15 is that you use mass 4 pi squared r over t squared, okay? But you have to watch the units. So this is going to, so here's the sun, here's the Earth. You're going to calculate that centripetal force to keep it in orbit around the Earth. I've given you the mass of the Earth, I've given you the radius. Now, how long does it take for the Earth to make one spin around the sun? 24 hours or 365 days? What'd you say? 365 days. Yeah, 365 days. So you're going to use 365 days, but you've got to change that into seconds. And when you change this into seconds, don't round that number. Keep all of those seconds and then round your final answer. Now, when you get to number 16, okay, when you get to number 16, you're going to use the same equation. So on number 16, what you're trying to figure out is, let's see, here's Al. So here's Al standing in the equator. So as Al's going around like this, you're going to try and figure out how much centripetal force is needed to keep Al moving in a circle as he goes around the Earth as it spins on its axis. So on number 16, what are you going to use for T? Tina, how long does it take for the Earth to spin once on its axis? Yeah. So on 16, you're going to use 24 hours. So on 15, you're going to use 365 days. On 16, you're going to use 24 hours. Okay? All right. So this lab is due tomorrow. Okay? So you all should be able to crank through the data. And then I'm going to send that data out. So everybody's kind of dependent upon you guys. So, ready? Let's go do science. Now, hold on, before you guys go, I'll give it to you when we're over there. Don't worry about it.